We're going to wrap up this section starting with a few more terms. So I've already talked about inductive reasoning. Now we're going to talk about deductive reasoning. Deductive reasoning works the opposite way as inductive reasoning. With inductive reasoning, you start with a few very specific examples and try to draw a generalization. With deductive reasoning, you start broad and then you're going to take it more narrow. So deductive reasoning is the type of reasoning that we use when we do mathematical proofs. So we start with a premise or a hypothesis. In the last example, that theorem that was proved, the hypothesis was that n is any whole number. That was our premise or hypothesis. The conclusion is what we are trying to prove. So again, going back to that last example, the conclusion that is n squared is either a multiple of 4 or 1 larger than a multiple of 4. That's the conclusion. When we go about proving something, we can prove something directly or indirectly. So with direct reasoning, our hypothesis says if P, then Q, then we show that P is true and conclude therefore Q is true. With indirect reasoning, we start with our if P, then Q, but we say Q is false, therefore P is false. So with direct reasoning, we show our premise is true, therefore our conclusion is true. With indirect reasoning, we say our conclusion is false, therefore our premise is false. So you've got two different directions that you can prove something. A lot of times when you talk about indirect reasoning, it's called proof by contradiction. And if you take a lot of math theory classes, you find that you actually use proof by contradiction quite often. Sometimes it's easier to show something is false than to go directly to show it is true. So we're going to look at this last problem-solving strategy tip where we're going to use deductive reasoning. We're going to prove something. So we're going to start with direct reasoning. It says, use deductive reasoning to show that if n is a multiple of 3, then n squared is a multiple of 9. So I'm going to do direct reasoning here. So my premise, n is a multiple of 3, and I want to prove n squared is a multiple of 9. So I'm going to use direct reasoning here. So if n is a multiple of 3, then we can write n as n equals 3k. Because that's what it means to be a multiple of 3. You're 3 times something. So, direct reasoning. If this is true, then we can say that n squared is equal to 3k quantity squared. Let me go to the next line, which is equal to 9k squared when you multiply that out, which is a multiple of 9. So that is a proof using direct reasoning. Now, the second one, we're going to use indirect reasoning. This says, use indirect reasoning to show that if n squared is odd, then n is also odd. So with indirect reasoning, we are going to assume the conclusion is false and show that that proves the premise also false. So let me show you what I mean. It says here, if n squared is odd premise, then n is also odd conclusion. So indirect reasoning, I'm going to say my conclusion is false. So we're going to assume that n is not odd, but that n is even. Okay, so I'm looking at the opposite of the conclusion. N is even. If n is even, then we can write n as 2 times k. Now, let's look at n squared. If n is equal to 2k, let me do a comma, then n squared is equal to 2k quantity squared, which is equal to 4k squared. 4k squared, let me go to the next line, is 2 times 2k squared. Okay, 2 times this, right? 2 times 2 is 4. And when you can multiply by 2, you're dealing with an even number. Okay, so I'm assuming that my conclusion is false, okay? So if n is even, then that says that n squared is also even, okay? However, we are told that n squared is odd. Thus, this is false, okay? And n must be odd. It's a proof by contradiction. So we found a contradiction there. Again, we assumed that our conclusion is false. That showed that our premise is false, but our premise is not false. Our premise has to be true. N squared has to be odd. Therefore, n is not even, n must be odd. That's a proof by contradiction. Said this before, talking about the logic and the truth tables. If this is something that kind of makes your head hurt a little bit, we're not going to be spending tons of time with proofs in here, but I do want you to get a taste of what's happening in the background, what mathematics are happening under the surface. You are, unless you're dealing with really, really bright elementary age students, you're not going to be dealing with this type of scenario with the kids. You're not going to be giving them these kind of proofs to do. But you do want to understand logical thinking. You want to have thinking that flows, that you're going from one true statement to the next. You don't want to have conclusions that are just coming out of nowhere. You want there to be good reasoning behind them. And that's the purpose of why we're talking about this here.